These are the lesson activities for Math 204, Section 1.7. Consider the family of differential equations given by dy dt equals y to the sixth minus 2y to the fourth plus mu. Our goal is to see what the solutions to these differential equations look like and how they depend on mu. We begin by investigating the graphs defined by the right-hand side of the differential equation, which we're going to call f sub mu of y. So y is the variable, but we have a different function f for every value of the parameter mu. So f sub 0 of y would be y to the sixth minus 2y to the fourth plus 0. Okay, so I want to graph this. So I'm going to use my graphing calculator and a little algebra to get this. So if I want to know its zeros, I would set that equal to 0. Y to the sixth minus 2y to the fourth equals 0. Factor out a y to the fourth. So you'd have y squared minus 2 equals 0. And your zeros are going to be at 0 and plus or minus root 2. So here, and root 2 is about 1.4. So here and here. And then it kind of looks like a W. Okay, so now that I have that, I want to draw a phase line corresponding to dy dt equals f sub 0 of y. So a phase line puts on the equilibrium points, which is the places where dy dt equals 0. So that was at 0, root 2, and negative root 2. There are my equilibrium points. And then any place where dy dt is positive, we put an up arrow. So on this part of dy dt, it's above the x-axis. So it's positive, so I'm going to put an up arrow down here, okay, to the left of negative root 2. So up arrow there. And then from negative root 2 to 0, and then from 0 to root 2. These are both below the x-axis, so I put down arrows. And then after root 2, I have an up arrow because it's above the x-axis. Okay, so now I'm going to add a graph, a vertical shift of this graph. And I'm going to shift it just enough so that these horizontal tangent lines at the minimums are going to sit on the the horizontal axis. So we'll have our W will look something like this. Okay, so that was very eyeballed. I never carefully calculated these minimums. Okay, so based on sort of this really rough sketch where these are at about negative 1, these would have to shift up 1, which means I didn't shift this peak high enough. It would need to go sort of up to about 1. There we go. Okay. So roughly, it looks like the mu that would shift it to create another bifurcation value is about 1. How do the graphs of f sub mu, which is y to the sixth minus 2y to the fourth plus mu, relate to the graph of f sub 0 that we drew above? They're going to be vertical shifts. Of f sub 0. Okay, to find the bifurcation value, note that since f sub 0 has a point tangent to the horizontal axis, mu equals 0 is a bifurcation value. So we already have a tangent to the horizontal axis. That is a bifurcation value because if you move the graph down a little bit, that y equals 0 solution will go away. And if you move it up a little bit, there'll be 2. Okay, so on the same axes that you graphed f sub 0, graph any other functions in the family that have a point or points tangent to the horizontal axis. Okay, so I'm going to go back to the previous slide and add in a graph. But it's a very rough sketch. So we would say mu approximately 1, like question mark, question mark. Okay, and to find the exact value of mu that gives that function, we want to solve these two equations simultaneously. F mu prime equals 0 and F mu equals 0. We want the function to equal 0 because I want the minimums to sit on the x-axis. And I also want the place where the horizontal tangent line is 0 to sit on the x-axis. So I have to solve both of these equations. So F mu is y to the 6th minus 2y to the 4th plus mu. I need that to equal 0. And I also need the derivative to equal 0. So I need 6y to the 5th minus 8y to equal 0. Okay, so I'm going to start with the equation that has no mu in it. Ultimately, I'm trying to solve for mu. Start with the equation that has no mu in it. There's only one variable, y. I'm going to solve for it. So let's see, I'm going to factor out a y cubed. Oh, because this is 8y cubed. There we go. So if I factor out a y cubed, I'm left with 6y squared minus 8. And then either y equals 0 or y equals plus or minus the square root of 8 over 6 or 4 over 3. Okay, so now I have three values of y. I want to plug those values of y into my other equation to solve for mu. So I'll start with 0. So if I plug y equals 0 in here, I get 0 to the 6th minus 2y to the, minus 2, 0 to the 4th plus mu equals 0. So mu has to be 0. All right, then I'm going to plug in positive and negative square root 4/3. I'm going to do them at the same time because my powers are both even. So whether I plug in a positive or negative, I'm going to get the same result. So I'm going to plug in plus or minus root 4/3. So I'm going to have plus or minus root 4/3 to the 6th minus 2 times plus or minus root 4/3 to the 4th plus mu equals 0. And now I have to solve for mu. Mu is the only unknown. Okay, so to raise 4/3 to the 6th power, that would be 4/3 to the 3rd power, which is going to give me 64 over 27. It's positive because I'm raising, whether this is positive or negative, we're raising it to an even power, so it's going to come out positive. All right, and then same thing here. We have a positive and a negative, but we're raising them to an even power. So I just have to raise square root 4/3 to the 4th power. And you get 16 over 9. So I have minus 2 times 16 over 9 plus mu equals 0. So just combining like terms, just add these two fractions and you get negative 32 over 27 plus mu equals 0. So mu is 32 over 27, which is approximately 1.185. So it's kind of close to the 1 that we had estimated based on our really rough picture. In addition to 0, which we already know is a bifurcation value because it has a tangent line right on the x-axis, a horizontal tangent line right on the x-axis. So this new value, we're going to call it B. In this case, it's 32/27, is a bifurcation value for this family of differential equations. So we're going to choose 4 nice numbers, one on either side of each bifurcation value. So we want to choose one a bit larger than 0 and one a bit smaller. So a little bigger than 0, we could do like 0.5 and negative 0.5. And then for B, we're going to choose one a little bit bigger. So remember B, 32/27 is about 1.185. So a little bit bigger, I'm going to go up to 2. And a little bit smaller, I'm going to go not down to 1. Maybe I'll do like 0.8. That's good. Just so it's not too close to the actual B value when I'm trying to draw the graphs. Okay, so on the same axes we've been using from the previous page, I'm going to draw the 4 graphs for each value of mu. One a little bigger than 0, less than 0, bigger than B, less than B, and label them. Okay, so here are my original 2, f sub 0 in blue, and f sub 32/27 in green, which is the bifurcation value of mu. And now I'm going to graph 4 more. Okay, so I'll do them in all different colors. When mu is 0.5, okay, so I'm just typing in the original equation, y to the 6th minus 2y to the 4th, and I'm adding a plus 0.5 and graphing it. So that's just going to shift my original blue graph up by 0.5. So I'm going to move the point that's at the origin is going to go up to 0.5. And then these zeros are going to go up to 0.5. And then the minimums are going to go up by 0.5. Right now they're at about negative 1.2, so they're going to go up to about negative 0.7. And then I just sketch the same shape. So in red, that is f sub 0.5. All right, let's see, black. We'll do f sub negative 0.5. So I'm going to take the blue graph and shift it down by 0.5. Every point goes down by 0.5. It's going to be about there. And then connect those with the same shape. Okay, and that's f of negative 0.5. All right, now I have to do f sub 2. So that is a vertical shift up 2 from the blue graph. So my highest point is going to be like here. And all my zeros are going to be there. Oops, that's a little over. Like that. Good. Okay. And then the minimums are going to go up by 2, and they're at negative 1.2, so they're going to go up to about 0.8. F sub 2, and then I have to do f sub 0.8, and okay, so this is a vertical shift up 0.8 from the blue graph. So I'm going to just move all my zeros, my x-intercepts, up to 0.8. Oh, that's not right. .4-ish to 0.8. There we go. Okay, and then negative 1.4-ish up to 0.8. Okay, so those are all my x-intercepts moved up. And then my minimums have to move up by 0.8. Right now they're at negative 1.2, so they're going to go up to about negative 0.4. There we go. All right, now I connect my purple dots with the same shape. All right, that's all the graphs that we were asked to draw. Negative 0.5. That is the black graph. And you see it is, that 0 looks like it's maybe negative 1.5. Yeah, negative 1.5. And it is positive to the left of it. It's positive bigger than 1.5 and negative in between. So we've got equal f of 0.5, that's my red graph. That looks like maybe 1.3 is the zeros. And like 1.3 and 0.7. 1.3 and 0.7. In between the equilibrium points, we're negative, and in the very middle, positive. Look at the 0.8, which is purple. I didn't label it, it's purple. Looks like the x-intercept is a little less than the 1.3 I did before. Let's just go with, I don't know, negative 1.25. Yeah, negative 1.25 and 0.9. That's my green graph. I only have two x-intercepts at about plus or minus 1.2. It is all positive. The entire graph is above the x-axis. That's my yellow graph. It has no x-intercepts, and it is entirely above the x-axis. Okay, next we're going to draw the bifurcation diagram for dy dt equals y to the 6th minus 2y to the 4th plus mu. So we want to label the set of axes below with y as the vertical axis and mu as the horizontal axis. And we're going to draw in vertical lines that at all the values of mu that we drew graphs for on the previous page. And then we're going to turn each of those lines into a phase line. Okay, so I want 0. Vertical line here at 0. And then I need a vertical line at 0.5 and negative 0.5. And then a little less than b was 0.8. A little more than b was 2. And let's see, b itself was about almost 1.2. Okay, so this is negative 0.5 and 0.5 are clear. This one is mu equals 0.8. Mu equals 32 over 27. And then the 2 is pretty clear. Okay, so we already drew the phase line for 0. We did that way back. There were equilibrium points at 0 and square root 2 and negative square root 2. And then we had up, down, down, up. Okay, for negative 0.5, I'm going to go back and look at the graph. Points at 1.5. And negative 1.5. And it's negative in between those two, so down arrow, and then up arrow on either side. Oops, that should be an up. Okay, for 0.5, go back and that. Okay, so 1.3 would be like here. Negative 1.3. And 0.7. So that's like here and negative 0.7. Okay, and then my arrows are on the outer parts. We've got up arrows. And so in the middle, positive, and then these are negative and negative. Okay, so the 0.8. Okay, so negative 1.25 would be like here. 0.9 is really close to 1, like right there. Okay, and then this is going to be up, down, down, and up, just following the pattern from the previous line. Okay, and then at the bifurcation value, 32 over 26, it's approximate. So 1.2 be like right there, and negative 1.2 about right there. I have all up arrows here. Up, up, up. And then for the 2, so I just put an up arrow on it. And then the last thing I do is I connect my dots with a nice smooth curve. And it should turn out looking something like a W. Something like that. Oops. On the 6 sets of axes below, use your phase lines that we just drew in the bifurcation diagram to draw graphs of solutions. So this is different because these graphs are T, Y. So these are solution graphs versus the mu Y graphs that we drew before that were just phase lines for the different solutions. So now I'm going to take each of those phase lines and like zoom in on it so that I can look at the solution in terms of T. So the equilibrium points for the negative 0.5 were about 1.5 and negative 1.5. Okay, so it's like here, so equilibrium solution. And then I'll draw a solution in between, above and below each of these. So I'm just going to pick random initial conditions. The origin is a convenient one. Between the equilibrium points, the arrow is pointing down on the phase line, which means the graph is decreasing. So it has to go down towards the equilibrium solution, and it came from the one above. And then if I pick an initial condition above the equilibrium solution, the arrow is pointing up, so on the phase line, so I have to draw an increasing function. And then this one, the arrow is also pointing up, so an increasing function, something like that. Okay, so for a mu value of 0, that had equilibrium solutions at plus or minus root 2, which is about 1.4. So I'll draw that in very roughly. Okay, and then it also had an equilibrium solution at 0. So we put that in. And then I'm going to choose an initial condition in between, above, and below each equilibrium and draw in a solution. So when I'm below the negative root 2, the lowest initial condition I put, on the phase line, there's an up arrow, so that means that this has to be increasing. All right, between negative root 2 and 0, there's a down arrow, so this is decreasing. Between 0 and positive root 2, there is a down arrow, so it's decreasing. And above root 2, there's an up arrow, so an increasing function. Okay, so when we're a little bit bigger than 0, that's the 0.5, we have equilibrium solutions at 0. Nope, not at 0. Sorry, looks like 0.7 and 1.3. 0.7, 1.3. I should have given you a bigger scale on these. And then negative 0.7 and negative 1.3. And then pick an initial condition above, between, and below all of those equilibriums. And you just use the arrows from the phase line to determine how to draw it. So this one has to be increasing because the phase line arrow was up. And then the next one down is decreasing. And then increasing. And then decreasing. And then increasing. Okay, at a little bit smaller than B, that was 0.8. And my equilibrium solutions were oh 0.9-ish and 1 point, I don't know, somewhere around 1.3. .9 and bigger than 1, close to negative 1, and below negative 1. They're very rough. Okay, and then I've got increasing according to the phase line, and then decreasing in between. I'll do it in another color so you can kind of see. Decreasing. And then increasing. Decreasing. And increasing. Okay, at the bifurcation value, there are just 2 equilibrium solutions. They look like they're about 1.25 and negative 1.25, something like that. We'll just say a little bigger than 1 and a little less than negative 1. And then pick an initial condition between, above, and below each of those. And this one is increasing. The one in between is also increasing. And also increasing. And then the last one has no equilibrium solutions to draw in. It's just an up arrow on the phase line, which just means that this is always increasing. So pick any initial condition you want, random initial condition, and draw an increasing function. It's impossible to know anything else about what it looks like besides that it's increasing. Okay, last question. Locate the bifurcation values for the 1-parameter family and draw the phase lines for values of the parameter slightly smaller than, slightly larger than, and at the bifurcation values. So this is similar to the problem we just did, except I'm not breaking it down into a million steps for you, and that is also less necessary for this problem because it's in this nice factored form for us. Okay, so dy dt is y squared minus alpha times y squared minus 4. To find bifurcation values, we need to simultaneously solve where this equals 0 and where its derivative equals 0. So I'm going to have to take the derivative using the product rule. So it would be first times the derivative of the second plus the second times the derivative of the first, and set that equal to 0. So my ultimate goal is to solve for alpha. So I'm going to look at, but I have two unknowns, alpha and y. I've got two of them in both equations. So I'm just going to start with the equation on the left and try to solve for y. So I get either y squared minus alpha is 0 or y squared minus 4 is 0. So y equals plus or minus root alpha, or y equals plus or minus 2. Okay, so y equals plus or minus 2 is relatively straightforward to plug into my other equation for y and solve for alpha. So let's just plugging in y equals 2. So I'm going to get 2 squared minus alpha times 2 plus 2 squared minus 4 times 2, set that equal to 0. So I have 4 minus alpha times 4 plus 0, so equals 0. So divide both sides by 4, and I get 4 minus alpha equals 0, so alpha equals 4. So that's a value of alpha. All right, and then if I plug in y equals negative 2, let's see what happens there. So I'm going to get 4 minus alpha times negative 4 plus 4 minus 4 times negative 4 equals 0. So here I have, again, 4 minus alpha equals 0, so alpha equals 4. So nothing new there. And then I should try plugging in y equals root alpha. Okay, so I have root alpha squared would be alpha minus alpha, times 2 root alpha, plus root alpha squared would be alpha minus 4, times 2 root alpha equals 0. So that term goes away, and either alpha minus 4 equals 0 or 2 root alpha equals 0. This one gives me alpha equals 4. I already knew that one. This one gives me alpha equals 0. So there's another bifurcation value. Okay, and I'm guessing negative root alpha isn't going to give me any new information, but let's check. Okay, so y squared would still be alpha. Yep, okay, that term goes away again, and you get alpha equals 4 or alpha equals 0 again. So those are our two bifurcation values, 0 and 4. Okay, our next step is to draw the bifurcation diagram. I've put in a mu dy dt set of axes here. I want to put in the bifurcation values that we just found at 0 and 4. And then I want to draw in lines a little smaller in between and a little bigger than my bifurcation values. Okay, so now I need to put in the equilibrium points on each of these purple lines to make them phase lines. Okay, so when alpha is 0, that's my first bifurcation value. dy dt is y squared minus alpha, which is just 0, times y squared minus 4, and I want to know when that equals 0 to find the equilibrium points. So that happens at y equals 0 and plus or minus 2. So I'm going to put in, I'm going to need some tick marks on the y-axis here. 1, 2, 3, 4. Okay, so y equals 0, 2, and negative 2. And then we have to put in up and down arrows. So again, I want you to look at this dy dt, which is this, but with alpha being 0. And when you are between 0 and 2, like let's say at 1, if y were 1, this would be positive and this would be negative. So the entire dy dt would be negative. Positive times a negative is a negative. So I put a down arrow in between there. Okay, if I were to put negative 1 in here, same thing would happen. I would have a positive, and then this would be a positive 1 minus 4, which is negative 3, so positive times a negative. I have another down arrow right there. Okay, and then if I put in a number bigger than 1, bigger than 2, like 3 or 4, let's put in 3. So this becomes 9, which is positive, and 9 minus 4 is 5, which is positive. So positive times a positive is a positive. And the same thing will happen down here. Okay, now I need to scratch this. Done with alpha equals 0. Now I'm going to look at alpha equals 2. Right, because I shouldn't have labeled this mu. In this case, the parameter is named alpha. Okay, so now I'm going to look at alpha equals 2. Plug that into dy dt, so I get y squared minus 2 times y squared minus 4 equals 0. And I have 4 equilibrium solutions. Y equals plus or minus root 2 and plus or minus 2. So I still have my 2's, plus or minus 2. And then root 2 is about 1.4. Yeah, about 1.4. Okay, now I'm going to plug in something in between positive root 2 and negative root 2, like 0. If you put a 0 in for these y's right here, you get negative 2 times negative 4, which is positive. So this is an up arrow. Okay, then something between root 2 and 2. So this is 1.4, this is 2, I don't know, maybe 1.5. I might have to put this one in my calculator. 1.5 squared minus 2 is positive, and 1.5 squared minus 4 is negative. Positive times a negative is negative. So I've got a down arrow here, and I would have another one here. And then if you plug something bigger than 2, like a 3, this would be positive and this would be positive, so you have an up arrow. Okay, now I'm going to do an analysis for alpha equals 4, which is my other bifurcation value. So I have y squared minus 4 times y squared minus 4 equals 0. and I just have two bifurcation values at positive and negative 2. Okay, if I put 0 in here and in here, you get negative 4 times negative 4, which is positive 16. So we have an up arrow in between there. And then if you put in something bigger than 2, like a 3, that's positive and that's positive. So it's all up arrows for alpha equals 4. All right, let's look at alpha equals 6. So we have y squared minus 6 times y squared minus 4 equals 0, and I get y equals plus or minus 2 and plus or minus root 6, and root 6 is close to 2.5. Okay, so I have plus or minus 2, same as all the others. And then also plus or minus 2.5. Okay, if you plug in a 0 for the y's, this is negative, so you have a down arrow. Sorry, up arrow, because negative times negative is positive. Okay, and then if you plug in something big, like 3, something bigger than 2.5, like 3, that's going to be positive, that's going to be positive, so we've got an up arrow here and here. And then I just need in between 2 and 2.5, like maybe 2.2. I'm going to have to put in a calculator. So 2.2 squared minus 6 is negative, and 2.2 squared minus 4 is positive. So negative times a positive is a negative. So I have down arrows here and here. And then last one, I have to do alpha equals negative 2. So I have y squared plus 4 times y squared minus 4 equals 0. Y squared plus 4 has no real solutions when that is set equal to 0, so I just have y equals plus or minus 2 again. And if you plug in a 0, this is positive and this is negative. Positive times a negative is a negative, so you have a down arrow. And then plug in like 3. So this is going to be positive and positive, so you have an up arrow. What happened to my down arrow? Down, up, and up. So there are all my phase lines. The last thing to do is to just connect the dots. Okay, so one thing that is a pattern that's jumping out is that there are always equilibrium points at plus or minus 2. So we'll just connect those. That was a little off. That was supposed to be a 2 right there. So I should have a horizontal line like that. And then another one at negative 2. I did a really bad job drawing these, huh? There we go. That's supposed to be a horizontal line at 2. And then I have sort of a parabola looking thing. Like that. That goes to that one. Kind of messy, but that's the idea. there's a nice, neat looking version of this in the solutions to your in your packet.